Okay. In the previous lecture, we talked about how to find the Euclidean distance of two vectors and how to find the norm length of a vector. And we now have dot product and cross product of two vectors. Okay? And we have this rule for finding the dot product of two vectors. You say if u and v be two vectors, then u dot v, look, it's denoted by dots. Okay? U dot v is norm u times norm v times cosine of the angle between the vectors. We need to have, this is the angle between the vectors. Okay? Look, here you have these two vectors. It says find u dot v. It says find the dot product of these two vectors. If the angle between them is 45 degrees, this is the angle between u and v. Here we use this rule. We say u dot v is norm u times norm v times cosine theta. So for this, we need to find norm u and norm v, and also cosine 45. What's norm u? Norm u is the sum of squares, all components in a square root. The sum of squares, all components in a square root. Here you have 0. The components of u are 0, which is 0 squared, plus 0 is 0 squared, plus 3 squared, which is square root of 9, and it is 3. This is norm u. And you also need to find norm v. Norm v is square root of. We do the same for vector v. We square all components and we find the sum of them in a square root. Yeah, it's 2 squared plus 0 squared, that's it, plus 2 squared. This one is. These are the components of v. We square all of them and then the sum of them in a square. This equals to square root of 4 plus 4, which is square root of 8. And you could write down this as square root of 2 times 4. 4 in a square root is 2, so you get 2 square root of 2. This is norm v. We now have both norm v and norm u. How to find the dot product of u and v? We say u dot v is norm u times norm v times cosine theta. What's theta? Theta is 45. What's cosine of 45? Say cosine of 45 is 1 over square root of 2 or square root of 2 over 2. Any of them. Let's see. It's 1 over square root of 2. Or you can say square root of 2 over 2. Both are the same. Any of these you can use. Okay? Now, we just plug norm u, norm v, and cosine theta here. What's norm u? It is 3 times. Norm v is 2 square root of 2 times. Cosine theta is 1 over square root of 2. These two are cancelled out. And we get 3 times 2 is 6. This is u dot v. As you see, in the dot product of u and v, we got only a scalar. We got only a value. So in dot product of any two vectors, we get a scalar. We get only a number. Okay? That's it. Here we have this. It's the same. This is u and this is v. Let's find the norm of u and v. Norm of u is what? Norm of u is length of u, which is 0 squared plus 2 squared plus negative 1 squared. It is 4 plus 1 is 5. Okay? Do you know how to get 5? It's okay. It's easy. Norm V is negative 1 squared is 1 plus 1 squared is 1 plus 2 squared is 4. That's square root of 6. Is it? Now, what is the cosine of 90?
Or did you get the 5?
Okay. We just square these components and the sum of them is for norm u. What we do? We say for norm u is square root of 0 squared plus 2 squared plus negative 1 squared. Okay, this equals to 0 plus 4 plus 1. So you get 5. And this 6 is the same, but it's for V. Okay? Cosine 90 is 0. Cosine 90 is 0. We say U dot V is norm U times norm V times cosine 90. And this equals norm U is square root of 5 times norm V is square root of 6 times cosine 90 is 0, which is 0. So the answer is 0. Okay? The answer is 0. This means these two vectors are perpendicular to each other. معناه وعمدوا vector student النسب. If two vectors are perpendicular to each other, as you see, the angle between them is 90. That means vectors u and v are perpendicular to each other. So if two vectors are perpendicular to each other, we say the dot product of those two vectors is 0. Okay, that's it. So what if the angle is not given? Or if it's unknown, how to find the dot product of two vectors? It's easy. We just multiply the components. We just multiply the components to get the dot product. Let me give you an example. Let U to be. Let's say U1 and U2. If this is a vector, and V to be if V1, V2. We say U dot V is, look here we haven't given the angle. How to find the dot product? We just multiply U1 by V1, which is U1 V1 plus U2 by V2. What if we have 3 components? Then U3 by V3 for 4 components and so. The same. Let's take an example here. If you have, let's say U to be 3, 0, 7, 4. Here we have 4 components. And V is also 4. In V, we have 4 components. Let's say 2, negative 5, 1, minus 2. If it says, what's U dot V? What we do? The angle is not given. How to find it? We just multiply the corresponding components. These two, these two, these two, and these two. Then sum of them. Okay? It's easy to find. We say 3 times 2 is 6. Then 0 times negative 5, 0 times negative 5 is 0 plus 0, then plus. 7 times 1 is 7 plus. 4 times negative 2 is minus 8, negative 8. Find the sum of these 4 values. We get 7 and 6 is 13, minus 8 is 5. This is the dot product of those two vectors. It's clear? Okay. So that we have n components in the vectors, u1 up to un and v1 up to vn. The dot product of them is u1 times v1 plus u2 times v2 up to un times v. That's all. It's easy. Here's four vectors with 3 components, and here we have vectors with 2 components. We took an example for 4 components. Here, it says, given this an exercise, u to be this, v to be this, w to be this. It says, find u dot u. You can find the dot product of a vector with itself. It's okay. It says u dot u. How to find it? You say 5 and -2 dot 5 and -2. You say 5 times 5 plus -2 times -2. That's all. Okay? How about this one? Find the length of u and then square it. Square the result. And for this, it's easy. Then you have cross products. In the dot product of 2 vectors, we get a scalar, as we saw before. Okay? But in cross product of 2 vectors, we get a vector. We get a vector. The cross product of 2 vectors is another vector. As you see that in dot products, we get a scalar. In cross products, we get a new vector. Here, in cross product of 2 vectors, I think we have studied how to find the determinant of matrix. Is it? We studied that. If we just know that, it's easy to find. It's easy to find. Look, in a 3 by 3 matrix, we have this matrix. If u to be this vector, u1, u2, u3, and v to be this vector, v1, v2, v3. Okay? Then, what's u cross v? Here, u is u1, u2, u3, and v is v1, v2, v3. And we have these 2 vectors. Then the cross product of these 2 vectors, first you need to find this determinant. It's easy. Just find this determinant and the cross product of those 2 vectors. But here, I, j, and k are components of any vector. Here, this vector could be written as u1i plus u2j plus u3k. These 2 are the same. Okay? Even for this one, you could write down this as v1i plus v2j plus v3k. Look, the first component is I. For the second component is j. For the third one is k. Now, what if we have, let's say u to be 3 minus 3, 4. How to write down this in the other form, on this form? You say it is 3i minus 3j plus 4k. That's it. Okay? So if u to be 4, 0, 2. How about this one? So u could be written as 4i plus 0j plus 2k. That's it. Okay? So any vector could be written as this or that. Okay? Now, what we do, as I said, if you have these 2 vectors, if you have these 2 vectors, u to be u1, v1, v2, U1, U2, U3, and V to be V1, V2, V3. Then, to find the cross product of those two vectors, what we do? We say I, J, K. Okay, we write down the components in this order: U1, U2, U3, and also V1, V2, V3. What we do? How to find the determinant of this matrix? If we use row 1, if you use row 1, to find the determinant of this matrix. What we say? We say it is A11. Let's say it's matrix A. It's A11, which is I, times. Now we remove these rows and columns. We studied this before, is it? What we get? We get U2, U3, V2, V3. It's always the same for all vectors. The cross product is the same as what I do now. Now, for this one, here for this one, we have it's -1. This is 1, 1. 1 plus 1 is 2, so it's positive. That's why we don't need to write down it. Okay, you say U cross V is this. Then, for this one, for the second one, we remove these two. Okay, we remove row 1 and column 2. What we get? But here we need to write down plus -1 to the power. What's the index of this entry? It's 1, 2, is it? It's in row 1 and column 2. So it's -1 to the power. 1 plus 2 is 3, so you get -1. It's minus J. What's left? These two and these two. If you remove row 1 and column 2, we got those two, those 4 elements. We get U1, U3, V1, V3. Okay. Then for the last one, it's K times the determinant of. Once we use that, we remove these two rows and vectors. What's left? U1, U2, these two, and these two, V1, V2. Look, if you just know these, that's enough for finding the cross product of any two vectors. Okay? Then what you do here? What's the determinant of this vector, of this matrix? It's a 2 by 2 matrix. What's the determinant of this 2 by 2 matrix? Minus V2 times U3. Yep. Great. We say we multiply these two, then minus, we multiply these two. That's the result. And for this one, the same, multiplying these two, minus, multiplying these two. And even for this one, multiplying these two, minus, multiplying these two. That's okay. Look at this. Look at this vector. These 3 vectors, I, J, and K, are the 3 vectors. It says, it's nothing actually. Here you have this vector, these 2 vectors. Look, it says if U and V be those 2 vectors, find the cross product of them. Here we need to find the cross product of U and V. How to find it? We do the same as we did above. We say U cross V is I, J, K. We write down U and then V. Okay, you also could write down V, then U. It's okay. Here 4 minus 9 and 1. Then 3 minus 2 7. What's this cross product? It equals to I times, look, these 4 minus 9, 1, it's U2, U3, and V2, V3. It's the rule that we have written down above. Then minus J. In J, we remove row 1 and column 2. If you remove those two, if you remove this row and this column, what's left? 4, 1, 3, 7. Then we have K plus K. Be careful, only the coefficient of J is negative. I and K are positive. K multiplying by, for K, we remove those rows and columns that K is in. Row 1 and column 3. So what's left? 4, negative 9, 3, negative 2. Now find the determinant of these matrices. It's I times 9 times 7, negative 9 times 7. It's minus 63. Minus 63. Okay? Then minus 2 times minus, it's for the rule, minus 2. It is minus 61, is it? The result is 61. So you get minus 61i. This is for the first component. As the determinant of that matrix, it's negative 61. Now, for the second one, we multiply these two, then minus multiplying these two. It's minus J times 4 times 7 is 28. Minus 3 times 1 is 3, which is 25J. So it is minus 25J. That's. Then, for the last one, multiplying these two minus multiplying these two. What's the multiplication of 2 and negative? 4 and negative 2? It is minus 8. Then minus 3 times minus 9. 3 times negative 9 is minus 27. Negative negative becomes positive. So it is plus 27. Minus 8 and 27 is 19. So you get 19K. This is the cross product of U and V. You can write down in this form. And also, you can write down U cross V is, just write down the coefficients of I, J, and K and separate them by comma. It's minus 61, comma, minus 25, comma, 19. That's it. This is the cross product of these two vectors. As you see, in the cross product of U and V, we got another vector. We got a new vector. That's it. You can either write down in this form or this one. Here we have another example. It's similar to the above one. Okay? Here, only U and V are changed. That's easy. And it's an exercise for yourself. Then we have linear combination. We have linear combination. What we do here, we say if we have a set of vectors, let's say V1, V2, V3, up to Vn, if these all are vectors, and let C1, C2, up to Cn are scalars. All C's are numbers, scalars. It says, if you could write down a vector in this form by multiplying a constant by the first vector, then plus a constant by the second vector, then plus a constant by the third vector, and so on. We say this vector is the linear combination of v1, v2, v3 up to vn. Okay? Even if you have v to be, let's say c1 v1 plus c2 v2. If you get a vector by multiplying the first vector by c and the second vector by c2, we say v is the linear combination of v1 and v2. Okay? Look at this example. It says, show that, it says, can you express u as the linear combination of v1 and v2 or not? Here we say, if we could find a value in which we multiplied by v1, and also if you could find another value, we multiplied by v2, and we find the sum of them. The sum of them is u. Then we say these two vectors are the linear combination. So u is the linear combination of v1 and v2. So let me tell you first what are the values minus 3 and 2. Look. We say u is c1 v1 plus c2 v2. If you could find, look, v1 is given and v2 is given also. What should we find here? We should find c1 and c2. We should find c1 and c2. We say we need to find a value here to multiply by v1, and also a value to multiply by v2, and find the sum of them. If you get u, means u is the linear combination of v1 and v2. Look, here we have given these two vectors, v1 and v2. We say u is, let me write down vector u is v1, sorry, c1 and v1 plus c2 v2. So what's vector u? Is equals to c1 times 1, 2, negative 1 plus c2 times 6, 4, 2. Later, تجمع الرياضي أمام كم? Which number should I multiply by this? And which number should I multiply by this to get this vector? To get vector u. Okay? If you could find c1 and c2, to multiply by v1 and v2 to get u, we say u is the linear combination of v1 and v2. Okay, let's replace c1 by negative 3. I checked it. Let's say it is negative 3, and this is 2. Okay, that means we could find two values, c1 to be negative 3 and c2 to be 2. I'm going to tell you how to find these two values. Okay, I've just checked at the end of the example. It's found that c1 is negative 3 and c2 is 2. Later, دوش من هي كليك داني في v2 بكين دوات الكوام بكينو كاتا u. Do we have two scalars c1 c2 in which we multiply them by v1 and v2 and find the sum of them to get u or not? Look, here we have if c1 to be negative 3 and c2 to be 2, let's check. Negative 3 times 1 is negative 3. Negative 3 times 2 is negative 6. Negative 3 times negative 1 is 3. Plus, for this one, 2 times 6 is 12. 2 times 4 is 8. 2 times 2 is 4. Find the sum of these two vectors. You must get U. And then you can say U is the linear combination of V1 and V2. Is U minus 3 and 12 is, what's minus 3 and 12? It's 9. 6 and negative 6 and 2 and 8 is 2. 3 and 4 is 7. Is this U or not? It must be U. Look, we got U. Yes. Where did you get C1 and C2? I'm going to tell you how to find C1 and C2. Okay? Now, it's important here to find only values of C1 and C2. So you are required to find values of C1 and C2. We now have some examples to find them. It's easy. We say for the first vector, here you have an example. It says, can we write down U and W as the linear combination of V1 and V2? These are V1 and V2. That means, can you find a value to multiply by V1 and a value to multiply by V2 to get U or W? Okay, we do each of these separately. For the first one, we need to say U is C1 V1 plus C2 V2. That means, see 9, 2, and 7 is equal to C1 multiplying by V1. It's 1, 2, negative 1. Plus C2 multiplying by 6, 4, and 2. Okay? We have these two. Now, we need to find the values of C1 and C2 here. We need to find the values of C1 and C2 here. We need to write down the augmented matrix for the system. What's the augmented matrix? It's important to write down the augmented matrix. And we studied that, how to write down the augmented matrix. We say, these two are the left-hand side elements. And here, this is the constant terms. We say, it is. First, we write down vector V1. V1 is 1, 2, and negative 1. Okay? And V2 is 6, 4, and 2. That's it? That's it. Times C1, C2, we have only these two, and now C1 and C2 is equals to 9, 2, and 7. This is the matrix form of the above system. This is the matrix form. How to write down the augmented matrix from this one? It's easy to write down. We say 1, 2, negative 1, 6, 4, and 2. Then we have 9, 2, 7. We write down them all together. We get the augmented matrix. Now, what we do? We apply the elementary row operations, produce row echelon form. Okay? How? We need to make this to 0 and this to 0 from this one. Okay? How to make this to 0? Yeah, we multiply it by negative 2 and adding to row 2. We say row 2 is row 2 minus 2 row 1. We get 0 there. And for this one, we say row 3 is row 3 minus plus row 1. If you add these two, look, it's 1. If you add this to negative 1, you get 0. That's it. For this one, you can watch the first video, I think. First or second video that we studied. Look, it is the reduced row echelon form is applied here. I'm not going to talk about this again because we studied this before. We get this. Okay? After the reduced row echelon form, okay, we apply the reduced row echelon form, we get this matrix. Look, in the third column, in the third row, all elements are 0. It's okay if all are 0. Then, in the second one, what this coefficient is for? It's for C2. As you see, the first column are the coefficients of C1. The second column are the coefficients of C2. Is it? As you see, that's it. This is C1 and this is C2. That's it. It's the first column and this is the second column. Now we say for, let's say C1 times 1 is equal to what? A -3, is it? Yeah, we say C1 times 1 plus C2 times 0. This times this plus this times this. This must be -3. Okay? How to get C1 here? This is 0. Because C2 times 0 is still 0. C1 times 1 is C1. So C1 is -3. It's how to find the value of C1. And also for C2. We don't get C1 in the first row. In the second one, we say C1 times 0 plus C2 times 1 is equal to 2. So from this, we get C2 is 2. And we already found that C1 is -3. Now, just write down them. You say U is -3 V1 plus, look, C1 is the coefficient of V1 plus in 2 V2. So you say, what's U? U is 927 is -3 times 1, 2, -1 plus 2 times 6, 4, and 2. That's it. This is, look, as we could write down U by a constant times V1 plus a constant times V2 means U is the linear combination of V1 and V2. We say U is the linear combination of V1 and V2. That's all. Then for the second part of the question, it's the first part, it's for you only. How about W? Can you write W as the linear combination of V1 and V2 or not? We do the same for W, okay? We do the same for W. This is W. It's V1, it's V2. W is C1 V1 plus C2 V2. Now we write down the matrix form of the vectors and then the augmented matrix. The augmented matrix is 1, 2, -1, 6, 4, 2, then 4, -1, 8. Then apply the reduced row echelon form here. Apply the reduced row echelon form. Okay? We studied that. That's why I am not gonna do it again. We studied the reduced row echelon form. Look, if you get some impossibilities. For example, if we get 0 and 0 here, and a value here, the value here, we say, that means if this number and this one are not both 0, and if they are different, we say it's impossible. Okay, for example, here 0 never equal to 3. Okay, what if this is 1? Is it possible? No, it's impossible also. 1 never be 3. Okay, but yes, okay, no problem for that case. It's okay. We could say in this case you say C2 is 3. If this is 1, it's okay. But if this one is 0 and this one is a value, is a value different from 0, we say it's impossible. Okay, 0 never be 3. So in this case, we say W cannot be written as the linear combination of V1 and V2. You say that. So in this case, we don't get values for C1 and C2. We don't get values for C1 and C2 because we got that 0 is 3. It's impossible. So in the solution of the linear system, this one, as you see, we have this. So this system has no solution. If it has no solution, means we have no values for C1 and C2. We don't get any value for C1 and C2. The solution of the system is the values of C1 and C2. Okay? The solution of this system is the values of C1 and C2. So if the system has no solution, means C1 and C2 has no any value. They have no any values. We have no values for C1 and C2. So it means W couldn't be written as the linear combination of V1 and V2 because here we cannot get values for C1 and C2. So W is not a linear combination of V1 and V2. That's it. So in this case, if we get some impossibilities, or if you get two different values for C1 or C2, okay, we say it is not the linear combination of V1 and V2. Look at this matrix. It says show that this matrix is a linear combination of these three matrices. That means we need to find a value to multiply by matrix 1 and a value multiplying by matrix 2 and the value multiplying by matrix 3 and find the sum of these three to get A. And then we can say A is the linear combination of M1, M2, and M3. So it's the same as before. But here, instead of having vectors, we have matrices. It's okay. Look, we say C times M1. M1, M2, and M3 are matrices, okay, which are given. These three. We must get A. This is matrix A, as I said above. Now, we enter this to here. We multiply all elements by C1, okay? And here also, we multiply all elements by C2. Multiply all elements by C3. Okay? Let's see what we get. If you multiply the elements here by C1, we get C1, C1. We get C1, C1, C1. So it's C2. These are the C2. C2, C2, C2. C3, 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 C3. Then we find the sum of these three matrices. Okay? What's the sum of these three matrices? here C1 plus this plus this. Okay, we add the same positions in all matrices. This here we get, and we equal it to this one. We equal it to this one. C1 plus 0 plus C3, we get that. Is it? C1 plus 0 plus C3 is equal to what? 1. So C1 plus C3 is 1. This is an equation. Then, here, we say this plus this plus this is equal to this. Is it? 0 plus C2 plus C3. So C2 plus C3 is equal to what? 1. Then this one plus this one plus this one is equal to this one. So this C2 plus C3, we got the same equation. So we just use one of them. Okay? We get the same equation as above. We get C2 plus C3 is 1. So we already found this. We don't need to write down it again. Then this one plus this one plus this one is 0, which is C1 plus C2 plus C3 is 0. We have these three equations. And you are free to use any method for solving these three equations. Yes. This one we equal to this position. Look, this position, this, we equal to this position. And others are all 1. Okay? Clear? Look, we got these three equations. Here we get 4 equations, but one of them is repeated. So we just use an equation once. We have these three equations, and you are free to use any method for solving this system. You can use Gauss elimination, Gauss-Jordan elimination, and LU decomposition or factorization. Okay? Any of these methods could solve this system. And also, you can use substitution. You can use substitution. For example, from the first equation, we get C1 is 1 minus C3. From the second equation, C2, write down all in terms of C1. Okay? Write down all the equations for C3, sorry. C2 is 1 minus C3. Now, we replace C1 and C2 here by 1 minus, sorry, C2. Write down C1 and C2 by 1 minus C3, and then let's see what we get. Okay, put in 3. Okay, if we replace C1 by 1 minus C3 and C2 by 1 minus C3, and we have C3 also, this is equal to 0. 1 plus 1 is 2. Minus C3. Minus C3 is minus 2C3. Plus C3 is minus C3. Is equal to 0. How to get C3? C3 is 2. We found C3. Now, plug it to here. We get C2. And plug it to here. We get C3. C1, sorry. And also, even from these two equations, put, let's name this to start. in star. What we get? C1 is 1 minus C3, which is minus 1, is it? C2 is 1 minus C3, which is minus 1. Now we got that C1 equals negative 1, C2 equals negative 1, and C3 is 2. So you could write down A as the linear combination of those three matrices. We can write down A as the linear combination of these three matrices, where C1 is negative 1, C2 is negative 1, C3 is 2. That's it. Okay? Here we have an exercise, it's for yourself. We now have linearly dependent and linearly independent of these two. Linear dependent and linear independent. This also depends on reduced row echelon form. Look, even the previous one, the linear combination depends on a reduced row echelon form. You should know reduced row echelon form, then you could prove or disprove that a vector is a linear combination of some vectors or not. Okay? Even here, in linearly dependent and linearly independent, we use reduced row echelon form or elementary row operations. We say if we write down, if you have v1, v2 up to vn, if these are vectors, v1 up to vn are vectors, we say these vectors are linearly dependent if we could write down as c1 v1 plus c2 v2. That means if we could find a value which multiplied by v1 and a value multiplying by v2 plus up to cn vn, it must be 0. If it equals to 0, that 0 is a 0 vector. It's a 0 vector. All components of that 0 is 0. Such that one of these constants is not 0. That means all the constants must not be 0. At least one of them must be non-zero element. It's okay if all are 0 and one of them is not 0. Okay? But the result must be 0. We say if all C1 up to Cn are not 0, we say V1, V2 up to Vn are linearly dependent. Linearly dependent. We say V1 up to Vn are linearly dependent. If not, C1 up to Cn are 0. But if the result is 0, the sum of them all. But if all are 0, we say V1, if we have only this solution, we say V1 up to Vn are linearly independent in this case. Look, linearly dependent if at least one of C's is not 0. But for linearly independent, we say all C's must be 0. All C's must be 0. It's okay. It's linearly independent if all are 0. If you have only that solution, if all are 0. It's okay, no problem with this. Okay. Look, here you have these vectors, v1, v2 up to vn. If you have these vectors, we say these vectors are linearly dependent or linearly independent if what? If we have C1 times V1 plus C2 times V2 plus Cn times Vn is equal to a zero vector. Look, that's it. And to write down this as the matrix form, we get this matrix. This equals to what? To 0. And here, this 0 means 0, 0, 0, n times. Okay? M times. That's it. This 0 means a 0 vector. It's equal to 0. That means all the constant terms here are 0. We solve this system and we get the values of C1, C2, and C3. Okay? Up to Cn. Look at this example. We have given V1, V2, and V3. It says, determine whether these vectors are linearly independent or not. Okay? Or linearly dependent. It's either these two cases. It's either linearly dependent or linearly independent. Okay? For dependent, we say if all C are not 0, that means if we have at least one C which is not 0, we say the vectors are linearly dependent. But the only solution is that all C are 0, we say the vectors are linearly independent. Okay? Then look, what we do here, we say C1 V1 plus C2 V2 plus C3 V3 is equal to 0. This must be 0. We need to find the values of C1, C2, C3. If all are 0, we say these three vectors are linearly independent. But if at least one of them is not 0, we say these three vectors are linearly dependent. How to write down these vectors as a matrix? We say V1, we write down as the first column, which is 1, -2, 3. And V2 is the second column, which is 5, 6, -1. V3 is 3, 2, 1. Multiplying by C1, C2, C3. As here, we multiply them by C1, C2, C3. This equal to what? Equal to 0, 0, 0, 0. Okay? We have three components in the vectors, so we just write down 3 zeros. Now, we write down the augmented matrix for this system. The augmented matrix is 1, 5, 3, -2, 6, 2, 3, -1, 1, and 0, 0, 0. That's it. This is the augmented matrix for the above system. Okay? Just a moment. Yes. فلما بعمل طاقة انت جلست باشا. Okay, let's take a break. Let's take a break now because we have only 3 more examples in this chapter. Here, we said we are going to write down the augmented matrix for the system. Now, we apply the reduced row echelon form for the system. We apply the reduced row echelon form for this system. Okay? This is what we did above up to here. We got this matrix. Now we apply the reduced row echelon form to get this one. We got this. Okay? So you should know how to apply the registration form and the elementary row operations. Okay, you should know that. We get this one. Then, from this system, it's in the registration form. It's in the registration form. Okay. Now, from the system, this is V1. Okay. We multiplied C1 by V1. Is it? We multiplied C2 by V2. And we multiplied C3 by V3. In the last row, we don't get anything because all the entries are 0. In the second one, what we get? C1 times 0. Okay, look, C1 times 0 plus C2 times 1 plus C3 times 0.5 equals 0. Okay, C1 times 0 is 0. C2 times 1 is C2 plus C3 times 0.5 is 0. We move this to the other side. We move this to the other side. So C2 is minus 0.5 C3. This means that C2 and C3 are not 0. C2 and C3 are not 0. Okay? Because C2 is negative half of C3. Okay? Then, in the first row, C1 times 1 plus C2 times 0 plus C3 times 0.5 is 0. We get C1 plus 0.5, C3 is 0. So C1 is minus 0.5 C3. Even here, C1 and C3 are not 0. That means C1, C2, and C3 are not 0. So we have at least one of those C which is not 0. Okay? Let's say C3 is not 0. That means we have at least one of those C, those constants, which is not 0. So as we get that, it means these three vectors, this means these three vectors are linearly dependent if not all these C's are 0. That means if we have at least one of the C's which is not 0, we say the system is linearly dependent. The system is linearly dependent. So V1, V2, V3 is linearly dependent. That's it. We have on the example this one. We have these three vectors in R3. It's already on the illustration form. That's it. Okay. We say C1 equals 0. C2 is 0. C3 is 0. In this case, all C's are 0. All C's are 0. Okay? All C's are, look, it's the same. It's vector 1. This is column 1. This is column 2. This is column 3. And you got this. Okay? You got this matrix. And from this system, we get that C1 is 0, C2 is 0, and C3 is 0. So as you see, all C's are 0. That means these three vectors, I, J, and K, these three vectors are linearly independent. They are linearly independent. That's it. Now you have another example. It's similar to the above ones. Here we have V1, V2, and V3. It's this determine whether these three vectors are linearly dependent or not. or linearly independent or not. What we do, we say C1 V1 plus C2 V2 plus C3 V3 is 0. Okay, it is 0. Then we write down the system. This is the system. Let me tell you how to get that system. If we multiply the first vector by C1, so first vector is the first column. It is the first column. If you multiply this by C1, what we get? We get 1 C1 minus 2 C1 minus, plus 3 C1 minus 4 C1. Is it? That's it. Then, for the second one, the second and the third, the second here and the third here, you got this system. Okay? You get that system. Now, you need to solve this system for C1, C2, and C3 and find the values of C1, C2, C3. If all are 0, means the vectors above are linearly independent. But if at least one of them is not 0, we say they are linearly independent, linearly dependent. That's it. This is the vector. Now, write down the augmented matrix, which is 1, negative 1, 1, negative 2, 3, 1, 3, 4, negative 2, negative 4, 2, negative 2, then 0, 0, 0, 0. Solve this. You get the values for C1, C2, C3, and all are 0. You get 0 for all. That means the vectors are linearly independent. The vectors are linearly independent because all the values of C are 0. Okay? And so it's the end of this chapter. If you have no questions, I go on to the next chapter. In the next chapter, in this chapter, we have some parts. Okay, in all, we talk about vector spaces. First, we have only definition of vector space and subspace. In this part of chapter 3, we just talk about vector space and vector subspace. We just study the definition of these two concepts and examples about it. Okay? We say V, let V be an arbitrary non-empty set of objects. That means V in V is a set of vectors. In V, we have some vectors, let's say V1, V2, V3, and so on. VU, those vectors, okay? In V, we have some vectors. We say, if the components of V satisfy two operations, addition and multiplication by scalar, if the components of V are defined for addition and multiplication by scalars. Yeah, it must satisfy these. These two are the conditions. Okay, the components of V should satisfy these two conditions. Okay, for these two conditions, we have some sub-conditions. We have 10 conditions actually. We have 10 conditions in which the components of V must satisfy to say V is a vector space. Okay? We have 10 axioms, 10 conditions to show that V or a set is a vector space. Look, First, we say if we take any two components in V, if we take any two components in V, so the sum of them must be in V, must be in V. Okay? The sum of them must be in V. But here, look, U, V, and W are vectors, but K and M are real values. They are values, numbers, K and M. We say, if we find the sum of two vectors, it must be in the space V. It must be in the space V. And it must be commutative with addition. Okay? If we have two vectors U and V, U plus V must equal to V plus U. U plus V must equal to V plus U. You must know these all conditions. Okay? You must know the conditions. In the third one, it's associative with addition. If we have three vectors, and if we add the first two, and then adding to the third one, it must be the same as if we add the last two, then adding to the first one. Okay? So if we have three vectors, it must be true that if you take any two of the three vectors first and adding to the third. Okay? With addition, it must be associative. It is associative with addition. These are three of the conditions. Okay? Three axioms of vector addition. Then, we must have the identity with respect to addition. That means we must have a vector in which we add it to any vector and we get the vector itself. Okay? Here we have zero vector. So zero vector, if we add it to any vector, is the vector itself. So it's additive identity. Then we have additive inverse. We must have a vector to add for another vector and we get zero. Look, we get a zero vector. U and negative U. U and minus U. These two vectors are inverse to each other. Inverse addition, additive inverse to each other, okay? With respect to addition, U and minus U are inverse to each other. For example, here, if we have 1, 2, negative 2, this is U. Minus U is minus 1, minus 2, 2. The sum of these two vectors is what? What's the sum of these two vectors? These two components is 0. 2 and negative 2 is 0. Negative 2 and 2 is 0. Look, we get a zero vector. That means this one is the inverse of that one with respect to addition. And also, we can say this one is inverse for that one. This is the 5 axioms for addition. And we have axioms for multiplication. We have 5 axioms for addition and 5 axioms for multiplication. For addition, we said U plus V must be in the vector. U plus V must equal to V plus U. Then it must be associative with respect to addition. Then we must have zero vector. We must have identity and inverse for each vector. Then for sixth condition or axiom is, we say if K is any real value, okay? If it is any real number, and if we multiply it by U, if u is any vector in V, it must be in V also. That means if we pick any vector in V, and if you multiply it by any real number, it must be in V as well. Then, if you multiply the sum of two vectors by K, it must equal to K multiplying by each of the vectors. So it is distributive. Okay, it must be true. Here, some of these are not true for some vectors. Okay, so if you have the sum of two real values multiplying by u, it must equal to multiply u by each of these two real values. And if we have the multiplication of two scalars was multiplied by a vector, it's okay if we enter one of the scalars into the vector. Okay, and we must have identity with respect to multiplication. With respect to multiplication, as you see, 1 multiplying by u is u. Okay, that means 1 is identity with respect to multiplication. So if a vector is a space satisfy these 10 conditions, we say the space is a vector space. Look, in some examples, if it is not noun, for example, if it says in Rn, it's noun. You know, it is n tuples. It is in Rn. The elements in Rn are x1, x2, x3, up to xn. You know that. But if it's a noun, the definition for addition and multiplication should be given. Scalar multiplication should be given. So the definition of addition, for example, adding two vectors should be given. And also multiplication of a scalar to a vector should be given. Okay? But these two definitions must be given, then we can apply the axioms. Look, in R, it says Rn is a vector space. Rn is a vector space. To show that Rn is a vector space, it must satisfy all the axioms. It must satisfy all the axioms. Look, the elements in Rn are in this form: x1, x2, x3, up to xn. Is it? That's the elements of Rn. It's all of these n tuples. Okay? Here x1, x2, x3, up to xn are real numbers. Look, the first condition says that the sum of two vectors must be in Rn here also. Must be in the space also. The space here is Rn. Let's say it is a vector. Let me check which vectors does V1 and V2, V3. Okay. Look, V1, V2, V3, up to Vn. This is a vector. And another vector is U1, U2, up to Un. Okay? Let's take these two vectors. This is V, and this is U. These two vectors must satisfy the conditions. Okay? And also let's take W also. W to be W1, W2, up to Wn. Okay? We say, if we pick any two vectors, the sum of them must be in the space. Okay? Let's check. V plus U is what? It's V1 plus U1. V2 plus U2. Up to Vn plus Un. Look, is this n tuples or not? n element تاعنا ثابت. So it's the same form as above, is it? It's the same. So this is belongs to Rn. That means it's closed under addition. That's the first condition. The second condition, we say u plus v must equal to v plus u. I'm working on the same. This u plus v. And can you say it equals to? Can you commutate these two? Commutate these two? Yes, it's two real numbers. u1 is a real number and v1 is a real number. So u1 plus v1 is the same as v1 plus u1. Is it? So v1 plus u1 is u1 plus v1. v2 plus u2 is u2 plus v2. Then up to un plus vn. What's this vector? It is u plus v. As you see, we proved that u plus v is v plus u. It's the second condition. Okay? The third one is associated. So let's take a break. Let's take a break, okay? We will finish after the break. Okay. We said if we take three vectors from Rn, they must satisfy all conditions or all axioms for addition and scalar multiplications. We have 5 axioms for addition and also 5 axioms for scalar multiplication. Now, what we do here, we say for addition, we prove that if we pick any two vectors, the sum of them is in Rn also. That means the sum of any two vectors is in Rn. If we pick the vectors in Rn, which are n tuples, so the sum of them is also a vector of n tuples. That means the sum of two vectors is in Rn, so it's closed under addition. Then we need to prove that it's commutative for addition. U plus v must equal to v plus u must equal to u plus v. V plus u is this vector. And here we have u1 plus v1 and u2 plus v2 up to vn plus un. Okay? Can you commutate with these two or not? They are real values. They are real numbers. Let's say it's 2 and 2 plus 0.5. Can I say it's 0.5 plus 2? Of course. Okay? That means here we can commutate these two values and these two values and up to here. So we get u1 plus v1, u2 plus v2 up to un plus vn. And this equals to what? It equals to u plus v. That means we proved that v plus u is equal to u plus v. This is the second axiom. Okay, that's it. That's the first axiom. And this is the second axiom. For the third one, it is associative. It is associative. Look, let's do that. Here, we say let me do it here. We say we must show that u plus v plus w is equal to u plus v plus w. These two must equal. We said u is u1 up to un. V is v1 up to vn. And w is w1 up to wn. Each of these vectors is an n tuples. Okay? We say u plus v plus w. It is u1, u1, u2 up to un plus v1, v2 up to vn. This is this bracket plus w. W is w1, w2 up to wn. We have this. We must prove that u plus v then plus w is equal to u plus v plus w. Okay? Now, this equals to what? This equals to u1 plus v1, u2 plus v2 up to un plus vn, is it? Then plus w1, w2 up to wn. Okay, now we add these two. We add these two. We say this equals to u1 plus v1 plus w1, u2 plus v2 plus w2 up to un plus vn plus wn. Now we can separate these together and u alone. Okay, what we get? We get u1, u2 up to un plus v1 plus w1, v2 plus w2 up to vn plus wn. What's this? Can you say it is v plus w or not? Yes. This is v plus w, and this is u, so it equals to u plus v plus w. V plus w both together. So we proved that u plus v plus w is equal to u plus v plus w. We proved this one. Okay, that's it. That's for the third condition. For the fourth one, we say we must have additive identity. Additive identity, and for the fifth one is additive inverse. For additive identity, we say if we add a zero vector to any vector, we must get the vector itself. Let's check. This is n tuples or are zero. The elements are zero. Plus u1 up to un. Can we get u1 up to un also? Yes, you get that. Look, 0 plus u1 is u1. 0 plus u2 is still u2. Up to 0 plus un is un. So you get u. And even if we add u to 0 vector, is the same. So we say 0 vector plus u is u plus 0 vector, and this u. In both cases, you must get the vector itself. So it's easy. It's just writing down the vectors. It's so easy. Then for the inverse, we say if we add any vector with the same vector in opposite sign, adding any vector to the same vector in opposite sign, we must get a zero vector. We must get a zero vector. Look, we say u plus minus u. We add u to the same vector in opposite sign. This is plus, and here this is minus. Adding these two, what's u? U is u1 up to un. And what's minus u? We just give a negative sign to all elements of u. Minus u is minus u1, minus u2, minus u3, up to minus un. Okay, that's it. It's minus u. U plus minus U is this one. Adding these is what? U1 minus U. U2 minus U2 up to UN minus U. So in all these cases, you get 0, 0, 0, 0, empty. So it's a zero vector. Even if we add minus U to U, we must get 0. In both cases, we get 0. So it is all the conditions or all axioms for addition. We now have axioms for scalar multiplication. We have five scalar multiplication axioms. We say if we multiply any vector by a constant, we must get a vector in the form of the vectors in the space. Look, if we multiply U by K, we get this. Is this n tuples? Do you have n elements in this vector? Yes. We just multiplied each element by K. Is it in the same form as the elements in Rn or not? Yes. So it is close under multiplication, scalar multiplication. For next one, if we have a scalar which is multiplied by the sum of two vectors, that means it must equal to Ku plus Kv. Okay, just put U and V as the vectors U1 up to Un and V1 up to Vn and multiply it. You get the result. It's easy. Okay, it's easy. Look, it's U, V. First adding U and V, and then K multiplying by this vector. Here, we multiply all elements in the vector. If we multiply K by this vector, we multiply this one by K, this one by K, up to this one by K. We get this. Okay? As you have the sum of these two real numbers. It's true for real numbers that it is distributive law. It's Ku1, Kv1, Ku2, Kv2, up to Kun, Kvn. We get this one. Okay? Now, we separate these. Ku1, Ku2, Kun. These are all together, plus Kv1 up to Kvn. Then, this is what? It's Ku. And this is Kv. As you see, we proved that. K times U plus V is Ku plus Kv. Okay? It's just taking time, actually, this type of questions. It's just, writing down a lot. It's easy. Therefore, others, for the last three conditions, look, let's return to the conditions. These are the conditions. For 8, 9, and 10, for these three conditions, we say if we have K plus M times U, U is U1, U2, up to UN. Okay? We must show that it's Ku plus Mu. Okay? Now, we multiply this by all elements here. We get K plus AM U1. K plus AM U2 up to K plus AM UN. Now, U1 multiplied by K and M. U2 multiplying it by K and M. UN by K and M. We get KU1 plus M U1, comma, KU2 plus M U2 up to KUN plus M UN. Okay? We now separate these two. It is KU1, KU2, up to KUN plus MU1, MU2, MUN. This is MU, and this is KU. Is it proof or not? Yes. It's easy. It's only, writing down, expanding, and then factorizing. That's all. Okay? Just expand and factorize. For all steps, even this one is the same. This one also is the same. If you multiply one by a vector, yes, a scalar multiplication. It's 1 multiplied by U1, U2 up to UN. So it's U also. Okay? It's U itself. So these are the conditions. So it means Rn satisfy all the axioms. So what can we say? We say Rn is a vector space. So if any space satisfy these same conditions, we say that space is a vector space. So Rn is a vector space because it satisfies all conditions or all axioms. Okay? Here's another example. It says the set V to be M by N. That means V is the set of all matrices of the size M by N. Of size M by N. It says this space is a vector space. Of course. Of course, it is a vector space. So the condition here is that the matrices that we get to be in the form of M by N. Okay? That means we must get M rows and N columns. Adding two matrices in this size, we get the same sign. We get a matrix in the same size. Okay? That's closed under addition. For closed under multiplication, if we multiply any matrix by a value, we get the same size matrix. And you can satisfy all the conditions here. It's easy. Okay? It's easy. You can satisfy all the axioms by this space. And so this space is a vector space. It is a vector space. And also it's in this book actually. We now have, look, I said this one, it's noun. It's any matrix of M by N. But if we have given the definition of addition and multiplication. If we have addition and multiplication definition, even in this example, it's generally, we know that it's noun. It says, let V be any function. Be any function. V be the set of all functions. We have the set of all functions. It says, is it a vector space or not? Is it a vector space or not? Is V a vector space or not? Here we have F. F is any vector, is any function. Here, V is the set of all functions. Okay? We need to show that V is a vector space. That means we must satisfy all the axioms by these functions. Let's see if you have f1, f2, and f3. We must satisfy all the conditions. What are the conditions? The axioms. We say we must show that f1 plus f2 is equal to f2 plus f1. Of course, it's true. It's true. This is the first one. Then, so it is the commutative. Before that, we have another axiom. We have f1, f2, and f3. We say f1 of x plus f2 of x must equal to f1 plus f2 of x. Of course, it's true. It's true for all functions. Okay. It's true if we have, let's say, f of x to be 3x squared. Let's say it's f1x. f2x to be 4x. We say if we find f1 of x plus f2 of x is equal to what? This plus that. So it's 3x squared plus 4x. That's it. How about f1 plus f2 of x? We just add them. It's the same. Even for evaluating a point, if we have f1 of 2 plus f2 of 2 is equal to f1 plus f2 add 2 or not? What's f1 of 2? Huh? It's 12, is it? Then plus. What's f2 of 2? This is f2. It is 8. It's equal to, the sum of them is 3x squared plus 4x. Add 2. If we replace this by 2, f1 plus f2 of x is this function. Is it? Let's replace x by 2 here. So f1 plus f2 of x is 3x squared plus 4x. What's f1 plus f2 of 2? If this is 2, we replace x by 2. What we get? It's 20. Is the left-hand side equal to the right-hand side? Yes. It means it's closed under addition. It's closed under addition. So f of x plus f1 of x plus f2 of x is equal to f1 plus f2 of x. This is the first condition, the first axiom. This is the second one. Okay, for the third one, see, it's associative. f1 plus f2 of x plus f3 of x must equal to f1 of x plus f2 plus f3 of x. Okay, the fourth one, it's easy to show this all. It's easy, that's why I'm not going to do it. For the fourth one, we must show that we have 0 plus f1 of x. It equals to f1 of x plus 0, which is f1 of x. Of course, 0 adding to any function is the function itself. Number 5, we must have inverse, additive inverse. We say f1 of x plus minus f1 of x is equal to 0? Of course. So you must show that also. Minus f1 of x plus f1 of x is 0. In both cases, you must get 0. It's 0, of course. Any function adding to the same function in opposite sign is 0. These are the axioms for multiplication. Sorry, for addition. For multiplication, the axioms of multiplication, we say kf of x as still a real value function or not. If we multiply a function by a value, do you get another function or not? Of course you get another function. Okay, so it is kf of x is in R, is it? It's from R to R. It must be in R. So if x be any value and k be any value, we get a real number. Okay, it is number 6. Number 7, if you have k times f1 of x plus f2 of x, this must equal to k f1 of x plus k f2 of x. Okay, it's easy to prove that. Then it's number 7. Number 8, we say if we have the sum of two real numbers times f of x, it must equal to k f of x plus m f of x, and it's easy to prove, to show that. Number 9, we say if we have km times f of x, it must equal to k times m. We can enter one of the real numbers into the function and the other one to be in the outside. Number 10 is if we multiply a function by 1, can we get f of x as well? Of course. Here it's just the rules. Okay, you need to give a little bit explanation in these steps. Okay, it's not the final answer for this question. Here in some of these, you need to give some explanation. Okay, explain it. And it's easy to explain them. Look at this. Here, it says let V to be this vector. Here, V and W are these two vectors. Here, V is the set of all vectors A, B, in which A, B are in R. That means the entries of the vectors, the entries of the vectors are in R. Here, V and W are both belong to V, to capital V. Capital V is the set of all vectors. Okay, what we do? If we pick two vectors from V, from space V, V is this vector and W is this vector. It says, look, here the definition is given. The definition is given. It says V plus W is what? It is the sum of first components plus 1. It's defined by this way. Okay, it's defined. We cannot say why it's added by 1. Okay, we cannot say that. It's defined. It's the definition. It's given. And these two plus 1. The sum of these two vectors, V1, V2, and W1, W2 is V1 plus W1, W plus 1. And also V2 plus W2 plus 1. This is the sum of those two vectors. It says, show that V satisfied axioms 1, 2, and 3. That means V satisfies axioms 1, 2, and 3. What are those 3 axioms? Axiom 1 says that You should know all the axioms in order, okay? Let me write down the axioms. Axiom 1 says that V plus W must be in V. It must be closed under addition. Okay? It must be closed under addition. The second, we say V plus W must equal to W plus V. That's the second condition. The third condition, it's associative with addition. Say V plus U plus W must equal to V plus U plus W. That's all. Okay? Here, this vector must satisfy these three conditions. If we have given this condition, this definition, this is the definition. So we say V1 V2 plus U1 U2 is equal to what? Based on this definition, what's the sum of those two vectors? It is V1 plus U1 plus 1, is it? Then U2, so V2 plus U2 plus 1. Okay? As it's given here, we must use this definition. We don't say it is U1 plus V1 and U2 plus V2. It doesn't equal to this. Okay? Because here the definition is given. The definition is given. Now, what if we add another vector for this one? Okay? Plus, let's say W. What we get? This is a component, the first component, and this is the first component. Okay? We say it is this component, let's say A, plus this one, W1, plus 1. Is it? The sum of two vectors is always the same based on this definition. First component plus first component plus 1, comma, second component plus second component plus 1. Okay? What we get? What's the sum of those two vectors? These two vectors is V1 plus U1 plus 1. This is the first component. And the first component here is W1 plus 1. Okay? We say first component here plus first component there plus 1. As you see here, first plus first plus 1. That's it. We always add 1 for the sum of any two components. Okay? Now, this is the first component. The second component is what? It is V2 plus U2 plus 1. This is the first component here. So the second component here. What's the second component here? W2. Then plus 1. So the result is V1 plus U1 plus W1 plus 2. V2 plus W2 plus U2 plus 2. This is the sum of U, V, and W. Okay? That's it. Now we need to show that this space under this definition satisfies these three conditions. So the first one is, you say U plus V is in V. Yes. Let's try this. Let's try if this space under this definition satisfies these three conditions or not. We let U to be U1, U2, U3. Sorry, U1, U2. We have only two elements in it, as you see. V is AB. And V is V1, V2. W is W1, W2. We need to first show that U plus V must be in V. That means in the sum of U and V, we must get a vector in this form. As you see, the vectors in V are in this form, AB, where A and B are real numbers. Okay? We take these vectors from V. These are in V. Here, U plus V is what? It's U1, U2 plus V1, V2. What's equal to? Based on this definition, what does this equal to? U1 plus V1 plus 1. Is it? Then U2 plus V2 plus 1. Is it in V or not? Is this a real number? Yes, because U1 and V1 are real numbers. So the sum of them is a real number. And adding 1 to it is still a real number. It belongs to R. Is this a real number? Yes. So it is on the form of AB, where AB belongs to R. That means it's in V, is it? It's in V. Look at the definition of V. V says that it's on this form where the elements are in R. Of course, it's in R. That means this vector that we got here is in this space. So it satisfies the first condition. So it is closed under addition. It's closed under addition. Then, for the second one, for the second axiom, we say U plus W or U plus V must equal to V plus U. U plus V is, I'm just going to write down the result. It's U1 plus V1 plus 1. U2 plus V2 plus 1. Okay? If we interchange these two places or if we commutate these two, what we get? V1 plus U1 plus 1. V2 plus U2 plus 1. Is this equal to V plus U or not? You bring it to front. So it's V plus U, so it satisfies the second. And for the third one, it's the same. Okay? For the third one, do the same. And also it's done here. It's the first one. It's axiom 2. It's also done. As the third one. U and V first, then adding to W must equal to V and W, then adding to U. It's easy. It's just expanding and factorize. Here it says V is in R. The addition scalar, the addition and scalar multiplication is defined by this. It says A plus B is equal to 2A plus 2B. That is, if you pick any two value as 2 times first plus 2 times second. Okay? And also for scalar multiplication, it is if we multiply any vector by k, it's k times the vector. It's the normal multiplication. It says show that addition is commutative but not associative. Addition is commutative but not associative. What's commutative? Commutative, we say if we have a plus b, it must equal to b plus a. What's a plus b? A plus b is given. It is what? It's 2a plus 2b. Can you commutative these two? Yes, it's 2b plus 2a. Can you say it is b plus a or not? Yes, we can. This is commutative. For associative, if we have three, let's say a, b, and c, say a plus b all plus c must equal to a plus b plus c. Okay, this must be equal. What's this? A plus b is 2a plus 2b. Is it? Plus c. Then you have this is, let's say it is d, and that's c. What's the sum of those two? It's 2 times first plus 2 times second. It's always the same. We apply the definition at all steps if needed. This is, let's say it is d, and that's c. What's d plus c? It's 2d plus 2c. Is it? Here we get 2 times this one plus 2 times this. So it's 4a plus 4b plus 2c. And let's do here also. It's a plus b plus c is what? It's 2b plus 2c. Okay? And this equals to. This is a, and let's say it is, this is d. What's a plus d? It's 2a plus 2d. We apply the definition. So it's 2 times a plus 2 times the bracket, which is 4b plus 4c. Is it equal to this one? No. They are not equal. That means these two are not equal, so it's not associative. This is associative with addition. This property, this axiom, is associative with addition. You should know the axioms and even their names. This is for addition, and this is for associative. Let me check. Okay, we have only this example. I'm just gonna explain it on the screen, on the solved one, which is solved here. It says, let V equals R3. And look, the definition is given. Adding two vectors is this. It's just normal addition. It's just normal addition of vectors. Okay? And scalar multiplication. If we multiply any vector by a scalar, we just multiply the first one, the top entry, by the scalar. Okay? For example, if you have, let's say 3 multiplying by 2, 1, 4, what does this equal to? We don't multiply all the elements. It's the definition. But actually here, if it's not given, if this definition is not given, we multiply this by all. But the definition is given. It says we just multiplied by the top one. What we get here? 614. We just multiplied by the first one, which is on the top. Okay? Look. What if you have 3 times 2 times 1, 3, 4. How about this one? If we enter this, what we get? Get 3, 2, 3, 4, is it? Again, if we enter this, we get 6, 3, 4, is it? If we have more than one scalar multiplication, we do the same procedure. We apply the same rule. Okay? We have these two definitions for addition and scalar multiplication. For addition, it's easy. It's the normal one. Okay? It's the normal addition of two vectors. First with first, second with second, third with third. So it satisfies all the axioms of addition. It satisfies all the axioms of addition. Look, axiom 1. It says, for axiom 1, we say, if we pick any two vectors, then the sum of them must be in the space. So what's the space? It's R3. It's R3. Okay? So the sum of two vectors must be in R3, is it? Look, these are two vectors. Let's say it's V and U. These are V and U. The sum of these two is this. Is it in R3 or not? How many entries do you have? This is 1, this is 2, and this is 3. That means it is in R3. Okay? The number of entries decide it's in which R. It's in R2, R3, or Rn, in which of them. Okay? So we have 3 entries. That means it's in R3. That means it's closed. V is closed under addition. Then for the second axiom, we say it is commutative. U plus V must equal to V plus U. Okay? Look, U plus V, here the addition is the normal one. These two, and these two, you get this. In real numbers, adding two real numbers is commutative. Let's say if we say 2 plus 3, it's the same as to say 3 plus 2. Is it? So these are real numbers. We can say it's x2 plus x1, y2 plus y1, z2 plus z1. Okay. Now we separate them. Once we separate them, v comes to front and you go to the last. Okay. For the third one, it's associative. It's easy. It's this. Just on. For fourth axiom, it is just 0 vector to adding to any vector is the vector itself, and also adding any vector to the same vector in opposite sign, we get 0. For axiom 6, look, it's scalar multiplication. If we multiply any vector by k, we get k times this. Is it in R3 or not? Yes, it's in R3. Because here we have 3 elements. We still have 3 elements, so it's in R3, so it's closed. Axiom 7, if we multiply the sum of two vectors by a scalar, we get this. If we enter this, we get this. So it is k. If this is u and this is v, we get ku plus kv. Is it? It's just expanding and factorizing. For the last one, we say if we have k plus m times a vector, that's it. That's it. So it is a real number. Let's say it is c. C times that vector is C times the top element. We just multiplied by the top element. That's it. But if we have, we say, we must show that K plus M times U must equal to KU plus MU. These two must equal. Okay? We have K plus M times U. We get this one. But once we multiply each one separately by that, we get K plus M, this one. As you see, the sum of these two, we get 2y and 2z in this case. So this doesn't equal to the above one. These are not equal. That means it doesn't satisfy the axiom number 8. So it's not a vector space. It's not a vector space because it doesn't satisfy one of the axioms. If it satisfies all the 10 axioms, then we say it is vector space. But if it doesn't satisfy only one of them, we say it's not a vector space. So it is. Here we have some exercises. Okay. We stop here, vector subspace. Okay.